Research Institute with them, and this is part of their birthday celebration. So, happy birthday to CNRS, and this is our way of celebrating it. It's through Kevin, who's going to tell us about the future of mathematics and how computers are going to get me out of a job by the sound of it.
Thanks for coming. So, a few years ago, my partner's mother died, and my partner and her sisters had to go down to the house in Kent and clear it out. She lived there alone, and so everything needed to go out so they could sell it. And they went through all the stuff, and they found lots of things. And one of the things they found, this is my partner's childhood home. One of the things they found was a box that belonged to my partner, and was in active use when she was a teenager. And it was the box where she kept her secrets. And it was a box. It wasn't this box. This is a random box from the internet. But that gives you the flavour of what the box was like. I mean, there was a lock on it, and the secrets were inside the box, and the box was locked. And of course, the key was nowhere to be found. And so all of this stuff came out of this house, and some of it ended up in my house. And amongst the things that ended up in my house was this box, which was plonked down on the kitchen table with no key, locked, as if to say, what now? And we'd just got a 3D printer for completely unrelated reasons. And so we could make stuff out of plastic. And I'm looking at this box, and I had a box as well when I was a teenager, and it felt to me like the kind of box I had was very, very similar. And, you know, I'm kind of looking in the hole and seeing, and I'm convinced that the key to my box that I had would probably open her box too. And I can kind of remember what this key looks like, because that's the kind of person I am. And but the thing is, my box, I won the box in the 1986 International Maths Olympiad. And there was a very elaborate key that came with it, or very fancy. I mean, there was a key that came, I'd given the box away. In 1995, I got a postdoc in the USA, and I took the box to Oxfam in Cambridge. So I was never going to recover my key, and she couldn't find her key, and the house was now empty. But I've got this memory of a key, and armed with that memory and a 3D printer, I think maybe we can open this box. So it's a long shot, but I described the key, which was relatively simple, really. I got a piece of paper and I did some drawings, and I described the key to one of my children, one of my sons. And my son took these drawings and then got some virtual clay. Fired up some software called Blender, and using the virtual clay that Blender offers you, he made, you know, a 3D model file of this thing that I'd sketched, which he then emailed to me, and I sent to the printer, and we printed out this little key. And I triumphantly brought this key in from the shed, and there's this hushed silence, and it doesn't even fit in the lock. It's a complete fiasco. Absolute failure. because I can't remember whether it's 2 millimeters big or 3. I mean, it was somehow, it needed readjustment. So back to the drawing board. So we go back to the piece of paper, and I'm saying, well, maybe we should make this a bit smaller, and it's all a bit of a mess. So the second one. So we come up with a second model. We print this out, and the second one fits in the lock, but it doesn't turn because you can somehow see I've made something else too big. And then the third one, we'd shrunk something, and then it was too small. So the third one did fit, and it did turn, but it didn't open the box. But you could kind of see that it was really trying to open the box. There was something that I knew was up there that it wanted to press. And so by the fourth iteration, the fourth key did actually open the box. To everyone's great astonishment, it did actually work. and the box was opened, and the secrets were unveiled. And we, just thinking about it later, you kind of feel that something magic has happened, really. Because we didn't have the key, we just had the idea of the key, and yet we opened the box. So the story sounds slightly more impressive than it is, because this isn't the key either. This is a random key I found on the internet. But this is not a particularly inaccurate representation of the actual key that I had to open my box. It was a sort of very, very elaborate, fancy end, but then a rather simplistic mechanism. And so that was the key that we were basically trying to make. And by the time it had gone into my son's brain and out of his brain into the computer, it looked something like that. So this is 3D modeling software. It's free and open source. Essentially every piece of software I use in this talk is free and open source. It's free open source software, and there it is. It's a key. It's living in some kind of virtual representation of three-dimensional space. And it's been made by someone, this is a complex tool, and my son knows how to use this complex tool, and he turned the piece of paper drawing I had into that virtual key. And then after that, the key gets emailed to me, and I send it. This wasn't the key at the time. This was me this morning thinking, wouldn't it be a good idea if I made another one? So this is me this morning, because I found the file, right? I found the file, and I sent the file to the 3D printer again. And there's my 3D printer in my shed printing out this key. I was using some very old ink, and I was in a bit of a hurry, so I set the speed to be very quick. And so that was what it came out as. So the end looks good, but this was just a lump anyway, right? The actual key, the real object somehow looked like that, but the thing we made didn't look anything like that at all. I've actually got it's here. It's a small rubbishy piece of plastic, but it did actually open a lock. So I just want to, so what is that? You might say it's a key, but I'd say it's not a key, it's a picture of a key. Is that a good thing? There you go. It's a picture of a key. And so I'm just going to trace what happened to this key and its adventure, or what happened to this idea and the adventure we had that day. So there was the actual key I once owned, which was a physical thing. And then that physical thing, who knows where it is, in someone's house in Cambridge probably, or in landfill. Then there's my memory of the key, which is just an idea stored in my own head. And brains are really complicated. So I don't really understand how this was stored in my head. But it was stored in a certain way where I last saw the key in 1995, and in 2015 I was asked to kind of remember what that key looked like. And I was like, oh yeah, that key was pretty simple. So that memory somehow survived for 20 years in some form. But on the other hand, you could ask, how many holes is this? The key I had looked pretty much like that. You got how many holes are there? 1, 2, 3, 4. I can't remember how many holes there were in my key. So the memory's degraded somehow. Oh, I've gone backwards. But anyway, my memory existed in some form, and then that memory was passed on to my son, and it was somehow stored in his memory. And then there was the computer file, and that was stored on a computer. That was a computer file. And then there was another computer file, which was, it was the same zeros and ones, but it was on a different, it was in a different computer's memory, the 3D printer's memory. And then finally, we got the yellow 3D printed key. So that was the root of this key. And it's interesting to also ask, I've kind of written down the objects, but there's connections between all the objects. So like, I had the key, and I would look at, my senses kind of told me, my senses turned the key into something in my brain, and then that memory was passed on to my son using pencil and paper, using diagrams and numbers. And then my son used a keyboard and a mouse to get the idea into a computer, and then we used email. We used the internet to get the idea from that computer to that computer, and then we used a 3D printer. We used some hardware to get that idea out. And in every single case, the idea changed. Because, you know, I don't have a perfect memory of that key. Witness the fact that the first key we made didn't even fit, because I couldn't remember precisely how many millimeters big it was. And when I sketched the, you know, but I did remember it had an elaborate end, but when I explained the key to my son, I didn't even bother explaining the elaborate end bit, because we just wanted something that worked. We wanted something that could be printed quickly. So information was definitely lost there. And then, you know, and then he had to turn some scrappy, he had to turn his, I don't know, it's what, I don't really understand what's happening there. We've turned it into something different. And then actually at this point, no degradation occurred. A computer file was sent on the internet, and all the zeros stayed as zeros and all the ones stayed at once. And that was kind of transferred perfectly, which is kind of interesting, isn't it? Once the idea is in that certain digitized form, it can move around incredibly quickly. You know, you could go to the other side of the world in under a second. And then, you know, and then we had this abstract thing that was all very perfect and beautiful and made out of polygons in Blender. And then when we printed it, it became a kind of a slightly crappy piece of plastic that, you know, that had lots of defects and, you know, little bits. Sometimes you have to sort of play with it and sandpaper off the errors. So, you know, it changed. In every stage, it changed, apart from one stage when the idea remained exactly. It moved, but there was no information loss. So that's an introduction, and now I'm going to talk about other kinds of ideas. Now I want to talk about mathematical ideas. So squares tile the plane, and that's kind of obvious. And if you're at school, maybe you kind of convince yourself of this by your teacher giving you lots of plastic squares, and you stick them together, and you know that might be enough to convince you that squares tile the plane, or if not, a piece of graph paper might convince you that squares tile the plane. So the idea is you can cover an entire infinite plane with infinitely many squares, and you know they all fit, and it's perfect, and it goes off to infinity. Squares tessellate. That's what I think. That's what they say. Is that right? Is that what you? There you go. Squares tessellate. We can tile the plane with squares, and what does that even mean, right? That's what we're told. And is this a proof that they tile the plane? What does that even mean? Because, I mean, what is this is a square, or is it? I mean, is it a square? And it's not even a square. It's got sort of weird bits where it can connect to other squares. What is a square? I mean, and what is a plane? And really, how can the claim is infinitely many squares tile the plane. But that can't be a statement about the universe we live in, because the universe we live in isn't infinite. Infinite is a really big concept. So it's sort of funny that we've got a tiling of an infinite plane by an infinite collection of squares. That can't be a statement about the physical universe. On the other hand, we've clearly got it's clearly an idea. We can store the idea in our head like we can store the idea of the key, right? So our brains are really clever, because they can store things like a key, but they can also store concepts like a square, which can't, or the concept that a plane can be tiled with squares, where a plane cannot possibly exist in our universe. So that's kind of interesting. So what is a square? You see, I mean, any kid would tell you that this was a square, but I mean, are all squares made out of plastic? It's sort of funny. This is some kind of universe representation of a square, but there's some other thing called an abstract square. And circles even worse. What's a circle? There's something subtle going on. There are round things, there are tires, and you could say those were circles. But there's something different, right? There's an abstract circle there. So we can store the idea of a circle in our brain, but can we store the idea of a circle on a computer? I mean, sort of probably. So I'm a child of the 1980s. So that's how I think of circles, because we used to play computer games, and there was some object and it's representing a football or a bullet or something, and we would call it a circle, but on closer inspection, you can see that actually that's not really very. I mean, if you stand along, maybe at the back you can't see what the fuss is about. Maybe it looks fine. But that was what we had to deal with, 80 by 24 in the 1980s, and now I've got my lovely 1,000 by 1,000 computer screen. I can have that kind of circle. So there's a much better circle, but actually I'm sitting here at the front and I can see that that's not a circle, because I can just see those squares that make it. It's sort of quite easy from here. It's probably trickier from where you are. So this isn't a perfect. That's a computer file. That's just some PDF on my computer. But it's not really a circle. It's quite a good approximation to a circle that we'll do in many real-world applications. But it's not a circle. Yeah. So there's the question: can we store a perfect circle on the computer? Because we seem to be able to store it in our brains. We can think about areas. We can do mathematics in our head with circles, even though circles can't really exist. We're doing something clever. We're thinking about things that don't really exist. So can we store a perfect circle on a computer? And because you see, the key existed, and we could have it in our brain, and we could have it on a computer. But perfect circles don't exist in this universe. We can store them in our brain. Can we store them on a computer? What's the difference between a perfect circle and a key? So we can store them in our brains, because brains are somehow clever. I don't know anything about brains. I don't know why I keep going on about brains. So we have to maybe figure out what a circle is. That's the first question. So what's a circle? And it turns out that the reason that we can't have circles is because there are irritating things like atoms and things in our universe that really get in the way of making a perfect circle. There's like quantum mechanics, and things get complicated when you get very small. And so let's reject the idea that perfect circles exist in our universe at all. They exist in our minds, but let's just take Plato's point of view. Plato said there was an abstract perfect universe of ideas, and let's call it the Platonic universe, and that's where perfect circles live. So that solves that problem. And the Platonic universe isn't some part of our universe, or it's some, in outer space or whatever. It's not part of our universe at all. It's just a different thing. It's an idea, It's not of our universe at all. Perfect circles don't exist in our universe. They exist somewhere else. So, and it has a precise specification, right? Has a precise specification, and it's an abstract object, and that's what the Platonic universe has got in it: abstract things. And so we saw Blender. That was where we had the key. Blender's a software that has this virtual three-dimensional space, and it can store representations of three-dimensional objects in our three-dimensional universe. It can store representations of physical objects as computer files. And there's some other software called Lean, which I'm going to talk about, which is software that can store representations of precisely specified abstract objects that live in the Platonic universe. And it can store them as computer files as well. So I'm going to explain how it's done, and it's a bit of a letdown, I warn you. So there's a circle. I mean, it's not really a circle because I can see the little squares to make it up. Thank you. There's a circle, center the origin, radius r. R is the radius, and all these points here are the same distance r. And then it's in the plane. The plane has an x coordinate and a y coordinate, so there's x and y. And so that distance there is x, that distance there is y, the radius is r, and this is a right-angled triangle. And when you have a right-angled triangle, there's the one theorem that everybody knows, because it's the only maths question that ever comes up in pub quiz. And it's Pythagoras' theorem. Pythagoras' theorem says that x squared add y squared is r squared. And so that means the formula for the circle is all the points x and y such that x squared add y squared is r squared. Okay? That's the formula for a circle. And so now we can switch over, as so many of you undergraduates have seen me do. We're going to switch over to Lean, and there it is. So I import data.real.basic. That's the number line. I need first of all, I need to make a plane, and to do that, I need to make the number line, but it's all right, we've got the number line. Somebody made that for us anyway. So we'll import the number line, and then we'll make the plane. The plane is something with an x-coordinate and a y-coordinate. So there's the plane. To make something in the plane, we need an x-coordinate and a y-coordinate, and now we need a radius, so that can be a variable there. And now here's the definition of the circle radius r. There. It's the points P in the plane such that the x-coordinate of P squared add the y-coordinate of P squared is r squared. And this is software like Blender, but instead of representing physical objects, it represents, instead of representing objects in the physical universe, it represents objects in the Platonic universe. So there it is. So you can, and I told you it was a letdown, that's how you represent an abstract pure circle as a computer file. So a circle's got a formula which describes it, and Lean just stores the formula. So there's an interesting bit though, in that Blender knows the laws of physics. You can sort of switch them on and off. The laws of physics weren't running when we were looking at that key, because that key was just sitting. If the laws of physics were running, the key would have just fallen down because it wasn't standing on anything. But Blender knows the laws of physics, and you can switch the laws of physics on, and then the things in your Blender universe obey the law of physics. And there's my talk from yesterday in Edinburgh. So what I instead changed to today's talk, where we find the thing that I want to play you. So this is objects in the Blender universe, and you've switched physics on. This is again my son. This is when he was learning about how to use physics and cameras in Blender. And it's just like these things don't exist, but you make them a bit shiny. You put a light on them, and there you go. And they're just sort of behaving. The first one was much heavier than all the others. Did you notice? And my son was just playing around learning about physics. We could just leave this forever, but let's not. Have you had enough? Shall I stop it? Is it yeah, okay, let's stop it. I mean, there's just, there's adventures to be had. So there you go. So there's Blender. When you switch the laws of physics on, it obeys the laws of physics. And Lean knows the laws of maths. And so you can use Lean to prove theorems about circles. But Blender, you can switch the laws of physics off and just goof, or you can change the laws of physics and make things do other things. But in Lean, you can't turn the laws of maths off, because Lean is actually a programming language. And the programming language, the commands in the programming language are the axioms of maths. So that's sort of the only thing you can do in the programming language is apply the axioms of maths. You can't turn them off, that's some of the point of it. So what you can do, like you can simulate physics in Blender, and you can somehow simulate the things we do in this department in Lean. You can prove theorems about objects. You can define objects, and you can prove theorems about objects by writing little computer programs. The computer programs don't do anything. It's kind of funny. Most computer programs you do because you want to see a picture on a screen or you want to see something. You run these computer programs and they don't do anything. They just they compile and they say, yeah, there were no errors. You correctly used the axioms of mathematics in that argument. So it's sort of an interesting. It's funny. It's not how people normally think about computer programs. You run it, and the only two things that can happen are there's an error or no output at all. And no output at all is like, yes, you won. No output at all means you just correctly applied the axioms of mathematics. So we can manipulate objects in Lean, but the thing is, someone has to make the objects first. So here's some examples of mathematical objects. Where's the clock? There's normally a clock there. Is it on the floor? Am I just being... Oh, thank you. Oh, it's on the table. And it says 8:30, and none of the hands are moving. Right. I just need some secondary... Oh, here we go. Oh, lovely. So here's some examples of mathematical objects. 2, that's a mathematical object. You thought that 2 was a thing that existed in the real world, but you're wrong, right? Things like 2 squares, that exists in the real world. two small plastic cubes that you learnt about 2 with when you were at school, but just 2 by itself, like 2 centimetres, that's fine, right? But 2 centimetres isn't the same as 2. 2 centimetres add 2 centimetres is 4 centimetres, and 2 centimetres times 2 centimetres is 4 centimetres squared. Right? 4 centimetres squared isn't the same as 4 centimetres. One's an area and one's a length, right? But 2 add 2 is the same as 2 times 2 because they're both 4. So there's the abstract 2. That exists in the Platonic universe. And the circle, we've mentioned that already. The number line, that's a phenomenally complicated object. You just treat it as red when you're at school, and then you go to university and you find out the definition. The number line is a really, really complicated object. The real numbers. Cauchy sequences, modulo equivalents, right? That's a bit of a shock. And then there's much more complicated things that we learn about in this room, in this building. We learn about fancy things like this. I tell people I'm a mathematician. Some people you meet, you say you're a mathematician, and they just imagine you spend all your days adding up gigantic numbers or something, because that's somehow that you know a certain amount of mathematics and you can't imagine that there's any more, so you just must be manipulating that stuff. But actually what happens is we invent more. I showed you how to do a circle. There's other things we can invent in that language. And so groups, rings, and fields are the things you learn about in the first year, topological spaces and in the second year, Banach spaces in the third year. Schemes are a master's course, and perfectoid spaces are what people do research in. Those are examples of mathematical objects. Every one of them will have a Wikipedia page with a formal specification, a formal definition. Infinite dimensional Banach spaces, I put that in just to show you that this virtual, this Platonic universe that people think about is not three-dimensional, right? There's like the cubes do exist in this Platonic universe, but so like the 4-dimensional objects and 23-dimensional objects and infinite dimensional objects, they all fit in fine because it's not really the kind of universe we live in at all. It's a very different thing. So all those objects are mathematical objects, and they all have very precise formal specifications, precise definitions. And that's somehow the important thing about them, right? There's objects in this world are slightly ambiguous. Objects in the Platonic universe, or at least the ones I'm talking about, are very, very precisely specified. And mathematicians play with those objects. Mathematicians have got a unique insight into that world, and they see beauty there. They see all kinds of funny things that it's really hard to explain to people that aren't mathematicians. And in it, they take things that we see in the real universe, like symmetry and things like that, and then they abstract it away and think, what's the most abstract notion of symmetry? And they invent things like groups, which is just an abstract, it's the symmetries of a thing, but there's not even a thing anymore. It's just its symmetries. Sort of funny. So it's a very strange place, the Platonic universe. And mathematicians study objects in it, and they study how objects behave, and they prove theorems about these objects. And that's what we do. And there's an example of a theorem. 2 add 2 is 4. And another example of a theorem. I'm going around to schools at the minute and giving talks called 2 add 2 is 4. And it's great. It's the kind of talks I like giving best are when students come in thinking that they know something, and they go out feeling far more confused about what's going on. Sometimes I actually actively try and achieve that when we're doing things like induction and things. And students come up to me at the end saying, I thought I understood induction, and now I'm all confused. And it's like, then I've made them think. 2 add 2 is 4 is harder than you think. You can prove it in Lean, and the proof is a few lines long, and you can get school kids to prove it. Pythagoras' theorem, that's a theorem. Fermat's last theorem is a theorem. It's kind of an interesting theorem, because Fermat's last theorem is a very simple-looking statement about almost the simplest kind of mathematical object, the positive whole numbers. And yet the proof of Fermat's last theorem is kind of thousands of pages long and involves vastly complicated mathematical objects in the Platonic universe that you would not imagine had anything to do with it. So how do we store these mathematical objects? So they exist in the Platonic universe, and then we somehow get them from the Platonic universe into our heads, into our brains. And then when we're manipulating them, we sometimes sit and do maths in our heads, and sometimes we actually use human language. Like we write sentences on pieces of paper, or we write all mathematical language. We write equations, and then we teach other people about these objects. We write books and give lectures, and we draw pictures. There's a kind of really, in lean you can't draw pictures because pictures aren't really part of formal axioms of mathematics. And that's quite interesting because sometimes we have very intuitive arguments that involve pictures, and then when you actually realise that maybe at some point somebody should check that these arguments do rigorously follow from the axioms of mathematics, it gets difficult. I know a lovely proof that every triangle is isosceles, that Fox's undergraduates year after year, and the lie is in the picture. So how do we manipulate these abstract objects? We often use pen and paper, sometimes draw pictures. And the question I want to ask really is this quite an old-fashioned idea? And one thing's for sure, it's what we've been doing for centuries. And that's exactly why it's old-fashioned, in my opinion. But people are resilient to change, and you know, well, maybe I'll move on. So photographs, the way we handle photographs has changed, right? Photographs used to be physical pieces of paper in photo albums. And then when computer screens got good enough that circles didn't look like that first circle, then people realized that it was worth turning a photograph into a computer file. And it became feasible to digitize photographs. And then the iPhone was invented, and then within a few years, everybody had a camera. The number of people, there's an XKCD about this, like the number of people walking around with a camera on them at all times. You know, the percentage of people just went from 0 to 100 in the space of a few years. And now you can digitize. Pictures. And the moment you can digitize them, you can carry them around really inconveniently, thousands of them. You can put them on the internet, and then there's Instagram. And you get people like my daughter who draw lots and lots of pictures and then take photos of them and stick them up on Instagram. And other artists look at my daughter's stuff and send their comments. It's quite, I don't know, I find it's quite interesting. And that could only happen because we could turn pictures into computer files. You know, you younger children might not realise that pictures didn't used to be computer files. Music is the next obvious example. When I was a kid, it was on vinyl or cassette tape, and people were very concerned, right? Home taping is killing music, they used to say. And they had no idea what was coming. You know, then came the CD, and then came the MP3, and then after that, instantly, music became infinitely much smaller to carry around. My old Sony Walkman, you put a tape in it, and then you've got 20 songs. And if you want 200 songs, you've got to carry 10 tapes around. That's quite inconvenient. And now you can just carry 200, so you don't think twice about carrying 10 years ago, you just put 200 songs on your phone, and that was great, or on your iPod. And then what happened then? Because music was just being stolen left, right, and centre, the entire music industry had to rethink its business model, and now we have Spotify. So now even 2,000 songs is a joke. My children have the Spotify app on their phone, and they have access to 2 million songs. Isn't that sort of funny? So digitizing music really changed the way it changed the very nature of how humans interacted with music. So digitizing things can change things really, really drastically. And so here's a question. Is it actually possible to digitize we digitized the circle, we just wrote down the formula. What about the complicated things we teach the undergraduates? Can we digitize that stuff? So I run this thing called the Xena project on the 4th floor, and undergraduates just come along and we just look at the kind of things they're doing on every Thursday evening during term. And we digitize bits of mathematics. So here's examples of bits of mathematics we've digitized. There's that nice easy lean doing the circles. This is a rather more complicated lean. This is a proof that every positive degree polynomial has a root. So those of you that aren't mathematicians just see something complicated here and something complicated here. Those of you that are mathematicians see something complicated here, because this is a complicated computer language. This isn't mathematics, this is something else. This is a computer language. This is, computer scientists might understand that. But on this side, if you're a mathematician, then you actually see something that might make some kind of sense to you. It says there's one goal, that's the thing at the bottom, and then it says f polynomial c, which means f is a polynomial with complex coefficients. Then there's hf, which is a hypothesis that naught is less than degree of f. This is the hypothesis that the degree of f is non-constant. F has got positive degree, and those are the hypotheses, and the conclusion is there's a complex number z such that z is a root of f. So that's that thing there that the mathematicians in the room understand. That thing there is a theorem that we teach the second-year undergraduates. But we certainly don't teach them this. This is computer science. This is mathematics. Computer science and mathematics are very related, but there's a computer science department next door to our department, and in the 20 years I've been there, until a few years ago, I'd never ventured into that computer science department. So there's the math side, and there's the computer science side. So who wrote this? Was it somebody with a PhD in computer science? This was a second-year undergraduate wrote this. A second-year undergraduate who comes to my club, and I taught him the language, and he went to Ari Laptev's second-year course and learnt this theorem that every polynomial of positive degree had a root, and to check he understood it, he wrote down the proof, not in the language that Professor Laptev used, the language of mathematics, using mathematical notation and English. He wrote it in a computer language. So the proof became a program, and you can just kind of click around, and you can watch how the proof goes. So the left-hand side is incomprehensible to pretty much, I say to pretty much everyone in the room, I see lots of people in the room who actually do understand the left-hand side, because they're my undergraduates. And so, we'll jump to a random point in the code, and now you see progress has been made. We only had 2 hypotheses. They're still there at the top. We've sort of got lots and lots of other hypotheses now. Like that hypothesis is that z0 is not a root of f. What's z0? It's a complex number. Anytime you want to know what anything is, you can just click on it, and it'll tell you what it is. So even though it looks complicated, it's not as bad as a book, where a book mentions something and you don't know what it means, and you're like, oh, it's been defined somewhere else. There, 0 is less than n, and there you go. Delta prime is a real number, and h delta prime 1 is the hypothesis that delta prime is bigger than 0. So he's proved lots and lots of things, and the goal has changed as well. The goal has changed. This says that f of z prime equals something else. So we've made progress both from the top and the bottom, and you keep ploughing through and you keep ploughing through. And if I click here, you'll see it change slightly, probably. There. I think the goal changed to nothing else. And I don't know, if I click down here, there, you see some things change on the top, and what was on the bottom's now gone off the bottom of the screen. And then eventually you go down to the very bottom here, and everything disappears, because the goal was proved. I thought this was great. I emailed this to the second-year complex analysis lecturer. And he said, what's the advantage of doing it like this over doing it in LaTeX? And I thought, you haven't really understood my point, have you? So, do you know, there's a very important thing. There's an absence of, look, let's do, cursors, it's compiling. There we go. There's a red line, right? And there down the bottom, it says 1 error, okay? And that means your proof is wrong. You see? And when that proof started, it was wrong because it was incomplete. And you change it, that proof isn't wrong now. We could type it all up the way mathematicians like to type it up, but there might be a mistake or there might be something missing. There's absolutely nothing missing here because the only thing that Lean knows is the axioms of mathematics. What now? Oh yeah, let's have a look at this. So I've been teaching this undergraduate course M1F, and I digitized all the example sheets. So I don't know, here's an example sheet. What shall I do? Here's sheet 5, hello. Oh, jeez. You just missed you. Look, that was 5 minutes ago. And there you go. There was some question about the Fibonacci numbers. It's very easy to explain to a computer what the Fibonacci numbers is. You just explain the question. There was a question about Fibonacci numbers being even or odd. You explain what it means to be even and explain what it means to be odd. And then you ask, is the 2018 Fibonacci number even or odd? And there's the question. I digitized the question. I digitized the solution. So that's what That's what the undergraduates had to go through this year, and occasionally I would pull out this thing and I would do mathematics in a new way. What next? Abby. So I digitised the exam, my last exam, and one of the undergraduates, is he here? Or am I going to humiliate him? There you go. Abby emailed me all the solutions to the exam. So this computer can get 100% on the exam I set last year, which I think is quite interesting. But it's got 100% in a very weak way. It's got 100% in the sense that it's first of all, it checked that all the questions were correct, which is nice to know. But secondly, it's I mean, the real issue is that it didn't generate the solutions itself. Abby generated the solutions and typed them up, right? So there's a next step after that, which is getting the computer to generate the solutions itself. We're not there yet. But one thing's for sure is it's somehow possible in some weird way. Here's an MSc project I did. Schemes are the master's level thing. This is MSc level mathematics. And I got a fourth year undergraduate. It was such a refreshing change. MSc projects in the computer science department, they're like, go and make stuff, make new stuff, write new code that's never been written before. MSc projects in the maths department, at least in pure mathematics, they're just like, go and get that, copy out the book. It's really, really, we have really smart students. And copying out the book is actually quite a good way of learning the material. And I gave this guy schemes and said, here's the book, now check it from the axioms of mathematics. And he made it. This is publishable. There are several other formal proof verification systems, and in every single one of them, no one has done schemes. And now one of our fourth year undergraduates made these schemes in Lean. This is publishable work. There's Kenny Lau. He's a first year undergraduate. This was his first year project. He formalised the local Langlands, the statements, not the proof, the statement of the local Langlands correspondence for tori. This was quite an interesting project. These are really, really complicated mathematical objects. And I just kept saying to him, all they are definitions. Just ask me what if you don't understand anything, just ask me, and I'll tell you what it means. So he just made a really, really complicated definition. That's sort of early PhD level. First year undergraduates. You get first year undergraduates going on about PhD level mathematics, and you kind of think you sort of half understand it, and you're just trying to show off. You do get people like that. I mean, I remember especially when I was at Cambridge as an undergraduate, and there were a lot of people trying to look much more intelligent than they were. But this is different because you can't say you don't understand it properly, because if it runs, then you've understood it from the axioms of mathematics. So, in 2012, a brilliant young number theorist called Peter Scholzer, he either invented or discovered perfectoid spaces. I like to think of mathematics as a big adventure through the Platonic universe. And Scholzer is a great explorer, and he discovered some amazing new things in this Platonic universe. Other people think about mathematics in a different way. So I think of Scholzer as a great adventurer. And he discovered some new things it's like discovering a new resource that were of great help to us. And using these resources, he brought them back to us. The ideas, he transferred this object into his brain, and then he wrote some things in the English language, even though he's German. He wrote some things in the English language and put them on the internet, and we all read them, and at the end of it, we all had some kind of model of a perfectoid space in our brain. And I wonder whether some degradation took place along the way. And Peter Scholzer used these perfectoid spaces to prove some brilliant new results in the Langlands philosophy and other things too in arithmetic geometry. And in 2018, he was awarded a Fields Medal as a consequence of his work. One of the highest honours in pure mathematics. There's somebody with a Fields Medal sitting in this room, but they're pretty rare. So I thought it was an interesting question to see if Lean could handle perfectoid spaces, because they were vastly, vastly complicated objects. And so I thought, let's try and make them. And I collaborated this. I've been doing a lot of collaboration with undergraduates recently, which has been quite extraordinary. But can Lean handle perfectoid spaces? This is a great test for the software. Can the software actually handle the kind of modern mathematical objects the modern mathematicians are interested in? And the answer is it could. Let's go back. There's our little website. There's our little definition. There's a perfectoid. So this is all lean code. There's our little definition of a perfectoid space. And it compiles. So there's nothing wrong with it. We've written down a rigorous definition. And we, mathematicians who don't know about this stuff are interested, so we've got some sort of hints. And one thing we did do is we made this weird little thing. The perfectoid space is the little star there, and all of these dots are theorems or definitions. And if you get up really close, then you're not going to be able to see this. But actually, this is a oh, you can't see it. Rotten luck. I can see it on my screen. There's lots and lots of tiny little lines that connect these dots together, but you can only see them if you're at the very front. And each line represents, a definition being used in a theorem, or a theorem being used to prove another theorem. So this is actually some incredibly complicated graph. Now, what is a perfectoid space? A perfectoid space isn't. I carry the idea of perfectoid space around in my brain, and it's not a really complicated graph at all. It's a infinite dimensional geometric object which has some property which has somehow been achieved by taking a limit over lots of covers. It's nothing like this. It's much bigger in some sense. This has got a finite number of dots. Perfectoid spaces have got uncountably, infinitely many points in general. And they behave in a very complex geometric way. So this is a really bad way for a human of thinking about what a perfectoid space is. However, it is a really good way for a computer to think about what perfectoid spaces is. And that's what I'm going to talk about in the last 10 minutes of my talk. In general, what's the point of digitizing mathematics? So one thing I've learned very quickly is, can it offer anything to the modern undergraduate? And here are some things which have been said in, directly to me or via emails or via, our official formal, our student evaluations. Leaders maybe think about, I think that's quite an interesting thing to say. No one's ever said that about my course before. And I didn't understand something, but I came along on Thursdays and I typed it into Lean, and now I understand it. That's another quite interesting thing to say. Here's another interesting thing. One of the lectures was almost entirely in Lean, and, please stop doing Lean. And that's not the only one. I got lots of things that said things like this, and I got several things that said things like this. And you can't please all the people all the time. And there is resistance to change. But one of the main problems really in practice is that if you actually want to learn Lean, then you have to read the manual. And the manual is written by computer scientists for computer scientists. And so we need another manual. So I'm going to spend the next 2 months of my life writing a manual for mathematicians. Because we desperately need one. At the minute, if you're a random 18-year-old kid doing a maths degree and you want to learn Lean, if you're at Imperial College, you talk to me. And if you're not at Imperial College, you've got a big problem. You've got a big problem. I mean, there are people in computer science departments that know it. There's a few other people in maths departments that know it. There's a guy in Sheffield that learns. There's not that many people around. So, but that's undergraduates. I think it has got something to offer undergraduates because it makes them learn mathematics better. And it's also very addictive, and it turns maths into a computer game. Every maths problem becomes a level in the computer game, and you solve the level. And when it says goals accomplished, you get a little adrenaline buzz if you're the kind of person that likes playing computer games. But most of the staff typically don't play computer games. Most of the staff are interested in pure maths research. And so what can it offer the staff? And currently it can offer the staff very little. And that's actually why I spend most of my time talking about this stuff to the undergraduates. Because they just have a different take on things. And as I say, the main point is I've turned a perfectoid space from a complicated geometric thing that only, certain number theorists can understand. I've turned it into a gigantic graph that isn't a very helpful way to think about perfectoid spaces at all unless you're a computer, unless you're the kind of unless you're the kind of thing that's very good at kind of manipulating combinatorial objects and trying to find one combinatorial object in another combinatorial object. So I don't think this helps for humans at all. I've done something that's of no use at all to humans. But people are interested in perfectoid spaces. It's a novelty. It's a PR stunt. Because, you see, perfectoid space is a graph, but everything is a graph. But actually, they're beginning to appear on the mathematical horizon. A guy called Tom Hales, who I was just spent 3 days in Edinburgh with, he proved the Kepler conjecture about 20 years ago. And the proof was so complicated, it involved thousands and thousands of calculations that sort of you ended up having to do, several thousand nonlinear equalities, and he checked them by hand and submitted the paper to the annals. And they after several years, they just confessed that they felt incapable of refereeing the paper because the proof was complicated in a tedious way. Right? Some things are complicated in deep, profound ways that you can try to get a feel for. But the proof of the Kepler conjecture says that if you've got a bunch of spheres and you want to spheres don't tessellate. You've got a bunch of spheres and you want to put them in a box. How should you arrange them? You should arrange them the way greengrocers arrange oranges. That's been known to greengrocers for centuries. But it was only proved, well, it's difficult to know when it was proved. Hales claimed he proved it, but then the referee said it involves checking several thousand calculations. If one of them's wrong, then the proof's wrong, and we're not going to check them all. And Hales reacted by saying, all right, then I'll get computers to check them all. And he typed them up into one of these theorem provers. So it's sort of funny, and that was the first real example of a new theorem being used where one of these theorem provers became essential. But this was a very extreme, specialized example. Most of the theorems we prove, you don't need a theorem prover because there was a very wide, shallow part, and a lot of the theorems we prove in the pure mathematics departments are kind of deeper and, they're sort of funny. But the next thing that'll happen is that we'll get really good search, and then more pure mathematicians will be interested in. And I'm convinced of this for a reason that's going to become apparent quite shortly. So I'm going to finish with 3 more case studies. And the first one is chess. Can you digitize chess? Yeah, you can. That's what it looks like. In the 1980s, chess was digitized, and people played chess on the internet, and that was what it looked like. And it was kind of cool. And you can guess what it means. I won't bother explaining it. But before that, in the late 1970s, my father brought a computer home from work that could play chess, and I was really excited because computers were rare in those days. They weren't in the home. He brought home this massive, great box and put it on the table in the front room. And I was very excited until I actually started playing the computer at chess, when I discovered that actually it was just incredibly slow and really rubbish at chess. And that was the late 1970s, possibly the early 1980s. And 20 years later, the computer chess program beat the world champion at chess. So 10 years ago, we had digitized pictures, as I mentioned, but the AIs that we'd written to analyze them, like this whole cat-dog thing, were not great. And then computer scientists realized that this was a phenomenally important problem, getting computers to work out what the picture is. And there were advances in the theory of convolutional neural networks, all from computer science departments. And then all of a sudden, computers were really good at telling what it was in the picture, and they could do it at such a speed that they could drive cars. That's not, that's actually true, right? It's not like they're going to come. They're driving around California right now, self-driving cars being driven by computers. They've killed one person. It was like a major news story. And like somebody dies in a car accident every day in this country, and it doesn't even make the news because everyone knows that people die in car accidents. So they can drive cars. They can drive cars much, much, much better than us. So it went from rubbish and then a good idea to much better than us. Very, very quickly. And in April, I used to be a number theorist. I still am. I know a lot of number theory, but I've been going to computer science conferences recently. And I was chatting to a guy over dinner at one of these computer science conferences called Christian Seged. He worked for Google. That's why search is going to get good. He works for Google, and he's very interested in digitizing mathematics. And he said to me that in 10 years' time, computers are going to be better than humans at proving theorems. And my job is to prove theorems. I've got two jobs, to prove theorems and to teach undergraduates. And he reckons that I'm going to be written out. He reckons I'm going to be replaced by a computer in 10 years. I don't believe him, but somehow I didn't really know who this bloke was. He was just someone I'd met at a computer science conference. So I looked him up afterwards, and this breakthrough paper on convolutional networks has got 30,000 citations. Christian Seged's top paper on Google Scholar's got 15,000 citations. He works in AI, and he just put something up today. I follow him on Twitter now. He put up something else. The problem with getting AI to do maths is that they need a massive, great body of mathematical theorems. And because we don't believe in this stuff, we've just written it down on paper and pen. We've written it down in natural language. So he thinks that they're going to be beating us at maths in 10 years. I think he's wrong, but there are people around him that are working very, very hard to make that happen, and they're backed by vast amounts of money and vast amounts of computing power. So humans talk about mathematics in languages like English. This is the problem. And computers talk about mathematics in languages like Lean. Computers are just another species, and they're like people from another country, and they speak a different language. But they're finding it really difficult to learn our language. Natural language processing is really bad. Getting computers to generate words that look like they've been written by a human, getting computers to write literature is very, very mediocre. And so if they can't learn our language, we could learn their language, and that's what I've done, and that's what I'm teaching the undergraduates to do, because it just makes it a step closer, isn't it? So what we'd really like to do is just take all our papers and just feed them in, and scan them in, and then they'd know everything we knew. So there's one big problem. They can't read our language, and even when they can read literature, they might not be able to read technical mathematical language at all. But on the other hand, because I learnt their language, I taught my laptop what a perfectoid space is. And it's just one step towards a really, really unknown future. Professor Laptev, who lectures this second-year undergraduate course, a part of which was formalized by Chris, he bumped into me in the corridor. Is he here? Ari, are you here? He bumped into me in the corridor late last week, and basically told me that he thought it was rather arrogant that anybody should give a talk about the future of mathematics, because we can't know the future of mathematics. So I don't think he's buying it. And he's right, of course, we don't know the future, but we can kind of look at the facts, and I don't know, and we can wait to see what happens. So that's what I'm going to do. But I'm going to try and join in. I'm sick of computer scientists doing it. I'm going to try and join in, and I'm going to get the undergraduates to join in as well. So I started with a story instead of saying thank you. So thank you very much for the invitation to speak, and thank you all for coming, and that's it.